Gabe, move the science guru.
Gabe.
Physics rules!
On this episode of Gabe Moo, the Science Guru, we're going to talk about the conservation of momentum while playing a bit of billiards.
In billiards, physics can be demonstrated in the collision between billiard balls. For example, if you had almost a perfect shot, you could have a collision that is near completely elastic, as seen in the demonstration that will be following.
So, looking at this video again, we see that when the two billiard balls collide, the collision is nearly elastic, so kinetic energy of the system is conserved before and after the impact. We also know that for any collisions between objects, such as billiard balls, momentum is always conserved. In this case, we see that all of the momentum of the cue ball is transferred into the striped green ball, causing the cue ball to come to rest while the colored ball continues its linear motion into the pocket. Of course, friction and other forces are acting on the cue ball, thus it does not come to rest exactly after it collides with the colored ball, proving the collision to be nearly elastic. However, if we shoot the cue ball at an angle towards a colored ball, we will not see a nearly elastic collision. Nevertheless, momentum is still conserved in the system. But will the ball make the pocket? As learned in class, when two objects interact, they exert forces on each other. However, the forces are internal to the system, so they do not affect the motion of the system during collision. Therefore, in the absence of these external forces, the momentum of the system is conserved. Now let us solve the problem to determine if the shot will pocket the ball. Using the tracker video and a protractor, we measured that the billiard ball must have an angle of trajectory between 20 and 50 degrees in order to be pocketed. Using the tracker app, we were also able to determine the initial and final velocities of the cue ball and the colored ball. Okay, so we're trying to find theta 2, and we're given theta 1, which we actually found by using a protractor and our video from tracker, and theta 1 is equal to 20 degrees. The initial velocity of the cue ball would be 61.57 centimeters per second, and then the final velocity of the cue ball, so the velocity after the collision, would be 41.03 centimeters per second. Now looking at the red ball, we can see that the initial velocity was 0 since it was stationary, and then the final velocity of the red ball, so after the collision, would be 24.82 centimeters per second. Okay, so we know that there's conservation of momentum in the system when the two balls collide, so we know that initial momentum is equal to final momentum, and the momentums would also be equal, the initial and final momentums would also be equal to each other in their relative x and y components. So the initial momentum in the x direction would be equal to the final momentum in the same x direction. So this equation can be rearranged using all the variables. And we know as well that using this diagram, we could come up with these equations so we can find out the actual x components of the velocities of the cue ball and the red ball.
And since we're using all of the balls being a relatively same mass, we can cancel out all the masses in this equation, which leaves us with this equation over here. And just plugging in our givens, we can rearrange the equation to find the theta, or the angle of the trajectory of the red ball. As mentioned before, we determined that the angle of trajectory of the ball has to be between 20 and 50 degrees, and since we determined that the angle will be 21.99 degrees, we know that the ball will end up going into the pocket.